Good day, everyone. It's a great honor to have Dr. Feng Yan here. I will give a brief introduction. So Dr. Feng Yan is currently associate professor with tenure at the School of Engineering for Transport, Matter, and Energy at Arizona State University. And also he's a director of Material Science Engineering graduate program at ASU as well. Before joining ASU, Dr. Yan is associate professor with tenure position at the University of Alabama. In addition to the academic experience, actually Dr. Yan has also working at the First Solar as a senior development engineer for the high efficiency cartel thin film solar cells. So his mainly research interest is focusing on the structural property and also processing relationships for the electronic and the photonic material and the devices for energy harvesting and conversion materials. So he has published more than 100 peer-reviewed journal articles, including Nature Energy, Nature Communications. And today it's a great honor we have Dr. Yan here to give us a talk on the highly efficient thin film PV for clean energy generation. Please join me to welcome Dr. Yan for this talk, and the floor is yours.
Yeah.
Thanks.
Thank you. Thank you, everyone. Thanks to Xiaojin's nice introduction, and it's a great honor to be here. So actually, I also appreciate that Dr. Hall and even for Kevin and invitation for be a senior visitor fellow in the UNSW for the School of PV and renewable energy engineering. So before I dive into my talk today, I really appreciate this opportunity to visit UNSW. So actually, I bring 4 undergraduate students from my US institute through the National Science Foundation International Research Experience for Students. It's a very great experience for the undergraduate student in the UNSW, particularly in Xiaojin's group working on the thin film PV. And also, we really appreciate the graduate student and the postdoc to give the lectures and the lab experience for this student. So I borrow this opportunity to thank Xiaojin again, and even Kevin, other graduate student and postdoc be here. So hope we will keep this one for the next 1 or 2 years to bring more undergraduate students from the US to experience the excellent research experience in the UNSW. So it's a very great experience. Thanks again. Yeah. So today I hope to share about my research for the thin film photovoltaics. And before that, I might cover a little bit for the climate change and why we work on the solar energy. Particularly the 2 topics I want to share. One is for the chalcogenide thin film solar cell, including the cadmium telluride and antimony selenide. Another one will be briefly introduced about a very low cost and manufacturable carbon-based perovskite solar cell and the related module fabrication. So both of these 2 thin film solar technologies have been commercial or close to commercial. So it will share about both the fundamental research and the potential manufacturing. And so the first thing, let me see why we work on the solar. So climate change is always a talk. It's become a hot topic in the news and everywhere. So it's not only dangerous for the animals, but for example here, this is the real temperature in Arizona right now. So it's close to 50 degrees C. And compared to Australia, that's one of the reasons we select UNSW, because here is the winter, we can escape the extreme heat, right? So some bad news is that because the extreme heat is really kill people. So last year, we have roughly more than 600 people died because of the extreme heat. And 2 weeks ago, you can see that a 10-year-old boy died during hiking because the dehydrate. So it's very dangerous, and you can imagine that how hot in Arizona. We will be there in 1 week, so it will be another dangerous thing. And major of this climate change contributed to the greenhouse gas emission. And you can see that from the carbon dioxide in the different industry section, and majorly for the transport, electrical power industry, and industry. So this is driving the government, not only US and worldwide, try to reduce the carbon emission and realize the carbon neutral. So different governments have the different goal. For example, here is the US, the government make a plan try to reduce the 30% of the greenhouse gas by 2030 and another one for 2050. So this is a very ambitious and aggressive goal because it's trying to balance the energy section and try to continue the economic growth. And if we revisit all this type of energy, renewable energy become the first candidate. And there are several types of renewable energy already being commercial, including the solar energy and the wind or even the nuclear. But the solar energy is the most available and free so renewable energy we can use, but it's also the safest energy. So this is a very interesting table that compare different type of energy production that people died. So because that's it's dangerous to make this manufacturing, and the solar is pretty promising. Even that's not the best greenhouse emission. So that's why we focused on the solar energy conversion and try to using the solar energy. More promising thing is that if we revisit the solar energy absorbing by the Earth, it's pretty nice is that almost 10 minutes of the solar energy received on Earth can support the whole year of the electricity used in the world. Of course, this is the ideal case. How to realize this conversion is still pretty challenging. And since compare the solar energy in the different countries, because the US have a very abundant solar energy in the West East, and that's why Phoenix area is so hot, right? So, but for the Australia, they also have a lot of solar energy can be used, and more countries have already generated a lot of solar energy to replace the traditional power plant. For example, China dominates about this solar energy and using the silicon module to generate this type of electricity already. And the US and Australia also have a very promising solar energy. So this is why more and more solar plants be utilized. And if we check about the future of the solar energy, because the manufacturing scale go larger and larger, then the price go cheaper. And recently it's about 3 cents or 4 cents for this electricity from the solar. But they also set up a goal to further reduce the cost. But this is a table from the Department of Energy, US Department of Energy. So it is very promising to compete with the traditional level power plant. And here is SU is actually the #1 sustainable energy to using the solar energy. And UNSW also have the solar panel installed on campus or use this technology. So this is a very promising area, and more researchers try to improve the conversion efficiency, the power conversion efficiency for the solar cell. And the very basic fundamental mechanism for the photovoltaic is already developed 200 years ago. It's not a new thing. Actually, it's just using certain material to utilize the photo generation and the photo recombination process to generate the electricity. This type of semiconductor material can be silicon or some cadmium telluride or even some emerging new materials. Here is the first solar panel 70 years ago, but the efficiency is just a single digit. But if you check about the solar panel, it looks similar, just the different of the size, right? But it's more and more people try to further engineer this material to increase the power conversion efficiency. Compared to the silicon and the thin film solar cell, we can notice that silicon even dominated the market now, close to 80% or 85%, but its manufacturing cost and the period is pretty long, spreading around 2 or 3 days, including the silicon ingot from the sand to the system. But here is an example for the cadmium thin film solar cell. You will see that it can be manufactured within 3 hours. It's like printing the papers, newspapers, pretty fast and scalable. And for the thin film PV, here is the structure of the cross-sectional imaging for the cadmium telluride. We can see that it's pretty similar to other type of techniques. And if you imagine that you make a sandwich in your kitchen, right? So it's just stacking different type of bread or different layer to realize the functionality. So overall, how we engineer this one, I may not extend too much because some of the experts be here. So measure the IV is one of the dominant technique to determine about the power conversion efficiency. Traditionally, we use the current voltage and to determine the open circuit voltage and also the let me open the laser point. So the short circuit current. So this is a very simple way to determine the power conversion efficiency by determining the voltage and the current. And meanwhile, if we check about this blue box and pink box, we can determine the fill factor. So this is how we determine the power conversion efficiency for all the PV techniques. But the different material have a different limit. Here is the theoretical limit for the single junction cells. For example, the silicon can achieve around 30%, but the cadmium telluride or the perovskite or even for the copper indium selenide have different band gap. So how we get the efficiency close to the theoretical limit is most of the research working in the PV area. So here is the cells. The solid line is the document about the champion cells, and the dashed line is corresponding to the larger module. So when the increase in the size and the more defect exist in the cells, so the efficiency will be also drop. So if we revisit the band gap to engineer the efficiency, majorly is try to trade off or balance about the voltage and the current. So higher voltage normally corresponding to the low current. Reversely, that the higher current may also contribute to the low voltage. So how we can engineer this voltage and the current is try to maximize the power output. So here is the documented power conversion efficiency for different type of solar techniques. You can see that in the past half centuries, more and more group and different company working in this area try to increase the efficiency. One of the major driving force to improve the efficiency is to try to reduce the cost. There is some relationship like 1% of efficiency improved can contribute roughly around 5% cost for the module. That's a huge money, right? So to dominate the market. And today I will try to share about the cadmium telluride and some emerging and perovskite techniques. The first is for the doping strategy in the cadmium telluride thin film. Cadmium telluride thin film solar cell is pretty unique. Compared to the silicon, you can check about the periodical table like the bubble, right? So we can see that the cadmium telluride is the only compound exists between the cadmium and the tellurium. And in the industry, we call it cadtel because it's short for the cadmium telluride. And we can see that several unique things drive this cadmium telluride technique. For example, it's compared to the silicon, it's a direct band gap, which is the promise about this higher light absorption. Compared to the absorption coefficient, this is almost 1 order of magnitude higher than the silicon. So this is why this cadmium can be a very thin film, roughly around 3 or 5 micrometer. But compared to the silicon, they need around 100 micrometer. So this is one very promising. And another thing is that many techniques have been used to grow this film. Including the physical vapor deposition solution process. Here is the efficiency chart corresponding to the past 50 years, roughly. You can see that the efficiency growth is very challenging for this technique. Initially, it's the single digit back to 1976. It's roughly around 10 efficiency. And stuck there for 10 years to jump around 10%. And more and more technique or innovations introduced to this technique and boost the efficiency. And then the last one, around the 16%, is around 1992. That's more than 30 years ago. So, and the stuck there almost 20 years, just 1% efficiency improvement. So I think most of you do not want to work on this one because you cannot graduate, probably. So, and since 2011, they demonstrate around 17% and commercial, and First Solar, one of the major companies work on this technique in the world, introduced a lot of investment and boost this efficiency from 17% to 22% within 5 years, which is very promising, and a lot of new idea and innovations was introduced. But you can see that it's stuck at around 22% since 2015, almost 10 years or 9 years. But this morning, they released a new record, 23.1. So this is a very promising and a lot of new technique introduced. So today I hope to share a little bit about my learning experience and working in this area for more than 10 years, how we can further engineer the efficiency and to see how we can break this efficiency. Major challenge in the polycrystalline cadmium telluride solar cell, since we call about the cadmium telluride commercial one is polycrystalline, grows using the thin film technique, including the sputtering, thermal evaporation, or whatever you call it. But the doped polycrystalline efficiency, for example, this January, they released 20.2, the voltage, open circuit voltage is stuck around less than 900 millivolt. That's 0.91 volt. But compared to its band gap around 1.5 EV, it still have a bigger voltage deficit. And another research direction is using the monocrystalline, which is the epitaxial cadmium telluride. It's a single grain larger film. You can imagine that no grain boundary impact inside this film. Good thing is that one of my colleagues in the Arizona State University, Dr. Yonghang Zhang, working on this area, grows the cadmium telluride using the MBE system, the molecular beam epitaxial system. We demonstrate around 1.1 volt. It's promised that the high open circuit voltage is accomplishable. So which is drive us how we close this gap between the polycrystalline and the single crystal, right? So, and if we can archive around 1 volt, then we correct the pathway to further improve the efficiency. And here is some prediction by leverage about the carrier concentration and the carrier lifetime within the cadmium telluride. For example, if we can further improve the carrier lifetime beyond 100 nanoseconds, or we can further increase the carrier concentration. Be careful is that the carrier concentration, we call it active concentration, not the incorporated carriers, dopants, because that will be a different way to mark about the carriers. This is actually our GPS, like to work on this area. So like you're using the Google Map to drive your way or set up different technique pathway. And we can see that whether we can get about 26% like silicon or the perovskite techniques, right? So we need setting about several of the metrics to increase the lifetime and the carrier concentration. One of the technique is the doping. Actually, doping is not a new technique in CadTel, but for all the semiconductors. It is trying to introduce the impurity in the semiconductor system, trying to manipulate about their carriers' behavior. For example, in the cadmium telluride, traditionally, probably in the past 50 years, they're using the copper doping. We call it group 1 doping, including the silver or even gold. They all try to occupy the cadmium site. Because based on the defect chemistry, we can see that the copper going to the cadmium vacancy can contribute an acceptor hole inside the system. Because the unique thing for the polycrystalline cadmium telluride is that the dopants is preferred to diffuse into the grain boundary. For example, here, so then you can further diffuse from the grain boundary to the grain innards. So this is the technique way. That's why a lot of work is trying to build the copper-rich layer on the back side of the film, then using the thermal to drive the diffuse. But this technique has several defects. For example, the copper diffusion will lead into the degradation of the module or the solar panel. And the module lifetime is around 25 years. That will degrade around 20% of the efficiency. How to extend this module lifetime from 25 years to 50 years? So then you no need to replace the module in the field, right? So particularly for the utility level PV, this is very promising for the power company. Another thing is that the copper doping fundamentally gives us the low carrier concentration. We characterize that the copper can only active less than 1% or even less than 0.1%. So that means most of the copper just stuck there without contribution to the holes. So that is the two major challenges try to retire the copper doping. So more and more groups try to work in another technique, because the good thing is that silicon only have one side you do using the P-type, N-type, but cadmium telluride have another side is telluride. So that's why we call it group 5 doping. Group 5 doping correct another chance to further occupy the telluride using the nitrogen, phosphor, arsenic, or even antimony binders. They have more freedom to tailor about the carrier environment. So for example, the theoretical prediction also give us the guideline that how we generated this group 5 doping. And in the past roughly 10 years, we cracked this way to initial about the group 5 doping. For example, the First Solar and the Unreal working try to using the initial in situ doping. Why we call it in situ? Because these dopants can be introduced during the film deposition using the vapor transport deposition or other way. So this is good is that the dopants is pretty uniform, and also the better control of the distribution because it's uniform during the deposition. But they also have some challenges, for example, the similar lower activation ratio for these introduced dopants, and also that generated the dopant segregation in the film. So almost 4 or 5 years ago, I collaborated with Dr. Feng Yan in the University of Toledo, trying to see if we can borrow the same concept like the copper doping from the back surface. So we call it ex situ doping or diffusion doping. And initially, it's very challenging because the group 5 dopant is difficult to introduce. Compared to the copper to the cadmium side, it's pretty challenging to drive the group 5 dopants into the tellurium side using the diffusion approach. But we succeeded this technique with efficiency roughly 18% previously, but we try to further engineer it. It's relatively easy, pretty similar to the copper doping, but we need to choose the unique or different dopant source. Here we try about the arsenic chloride using the solution, but be careful, this is a very toxic compound, do not operate in air or without any protection. Another thing is that this compound is easier to hydrolysis in the air, so we try using the nitrogen protection in a glue box and coating this layer on top of this cadmium chloride treated polycrystalline. Because the time limit, I may not introduce the cadmium chloride treatment process. But this one is pretty interesting is that this realize a low temperature diffusion for the arsenic ions into the polycrystalline cadmium telluride. And the result is surprise us initially why it works. And if we revisit about the chemical distribution inside this polycrystalline, we find the similar behavior like the copper ions doping. The arsenic ions can initially drive into the green boundary and then using the extra thermal to drive to the green inner, which were demonstrated using the second ion mass spectrum two-dimensional mapping. And also that further characterization demonstrates that the similar diffusion profile, like compare the arsenic and the copper, you can see that the copper, the arsenic is very heavily doped on the back side and light doping in the front side. So this is the desired doping profile to achieve a better back surface. The chemical inside, we can find another interesting thing is that because if we want to occupy the tellurium side, it's prefer an anion inside the system. But we're using a cation system in the arsenic chloride. How this reduction occurred in the system is still a little bit unclear, but per the chemical state understanding, it seems that the arsenic 3 plus cation convert or reducted to the arsenic 3 minus, which is pretty promising. We are working on this, trying to understand this process. And if the arsenic 3 plus work, and this will correct another way to using other group 5 dopants using different precursors. So further device characterization demonstrates that this arsenic chloride can be similar to the copper chloride, but the different environment protection. And the device is pretty nice, around 18%. This also demonstrates in different device architecture and demonstrates the carrier lifetime within more than 20 nanoseconds. But we'll see it's not that higher as expected because we try to further demonstrate high VOC, right? So this is the first try to using the ex situ diffusion process to realize the group 5 doping. And further characterization demonstrate a higher activation ratio if we determine the carrier concentration using the capacitor voltage technique and then combine the second ion mass spectrum, we can demonstrate that the activation ratio close to 6%, which is promising than 1% for the copper or other in situ. But we expect it can be further improved by tuning the processing or the device architecture, so it is ongoing work. And for the future of the cadmium telluride, efficiency is still one of the major goals compared to the silicon or the perovskite, which is already above 26%, right? So in the US, we have a cadmium telluride consortium, which is working together with the industry, national lab, and the university. So we set up a goal for 24% around 2024. It's a pretty ambitious goal, and 2026 around 26%. No matter how high the efficiency, but we close to there. So because we can leverage the industry resource, try to further unlock about the efficiency loss. But a good thing is that, like what I mentioned, this corrects the way to use other group 5 salt. After this arsenic chloride, we continue the collaboration and initiate the research agreement with the first order, and we demonstrate that using the bismuth can reach around 900 millivolt, and this is work is in revision right now. Hope so we can further continue this one, and we have an ongoing research project working with the NREL to continue this group 5 doping in the cadmium telluride, and we have some other techniques try to further realize about this technique. Continue for the material side, increased efficiency is pretty challenging. You can imagine that in the past 50 years, right, the efficiency gradually improved. But there is some other challenge for the cadmium telluride. For example, that the cadmium is pretty toxic. Even it's not that water dissolvable like the lead or some mercury, but it's still toxic, right? The recycling of the module and the generated actual cost. Another challenge is for the tellurium, which is the Earth's scarcity. It's like the rare earth element in the Earth. It's predicted that if we do not recycle all this cadmium module, all the tellurium reserve in the Earth can only last around 20 years. So this is the higher risk from the supply chain, right? So it's needed the different technique to replace this material. It's a bigger problem, but it's also create some opportunity for us to work in the university. So whether we can develop some low toxic and earth abundant light absorber material similar to the cattail, this potentially create additional backup for this technique or new opportunity. So this is why I try to briefly talk about the antimony selenide using the similar growth technique like the closed space sublimation for the cadmium telluride to see if we can demonstrate another technique to replace the cadmium telluride in the long-term run. So if we check about the cadmium, like what I mentioned, that tellurium is a pretty earth scarcity. So it's like the other rare earth element. So it cannot survive the 100 years manufacturing, right, without recycle. So First Solar can recycle 90% of the cadmium module, so make it more sustainable. But if we revisit about this table, we can find that antimony and selenium is pretty earth abundant. And meanwhile, antimony is pretty healthy. It can be used for medicine, so it's not that toxic like the cadmium. So another thing, if we want to grow as the material view, we can find that good thing is that from the phase diagram, because I'm a material scientist background, phase diagram is another guideline help us to evaluate the material thermal behavior. Cadmium telluride is the only compound between the cadmium and the tellurium. So, and a pretty high melting point, you can see that close to more than 1000 degrees. So that's the manufacturing cost a lot of energy because you need to vaporize all of this compound at a high temperature. But for the antimony selenide, good thing is that it's pretty stable, also the only compound between the antimony and the selenium. And the good thing is that it have a relatively lower melting point, just half around the cadmium telluride. So that's mean that we can use a very low manufacturing temperature to vaporize this compound. Another thing is that it's also tunable band gap like the cadmium telluride. We introduced the different type of gradient absorber in the cadmium telluride, like coupling with the cadmium sulfide or the cadmium selenide. Similar thing for the cadmium selenide and the cadmium sulfide, it also can be tuned the band gap to absorbing more or less light. So all of this similarity, this is why we initiated this project roughly 5 or 6 years ago, prior to using the cattail technique for this material. But the difference is that, or the unique crystalline structure for the antimony selenide is the conceal one-dimensional ribbon structure. So, so this is correct some challenger to growth this film like the cadmium telluride, because you can see that cadmium telluride is pretty 3D cubic. So it's very less limit for growth this film in a high quality material. And we tried to grow this one, and based on this technique, we evaluate about the growth technique. It seemed like a very promising candidate to bridge the gap between cadmium telluride and low toxic and earth abundant material. But it's a pretty challenger. Initially, we grew this film. The first graduate student in my group is almost crying because when they see this film, right? So it's no way to make a good device. The efficiency is 0, right? So it's a pretty challenger. You can see that the film looks like a needle. It maybe looks like some flake. It's also like some rod. The film, if you put the film face the light, it have a lot of pinhole. You can see that. But after you tune about the growth condition, here is a very simple closed space sublimation. You can put the powder inside and vaporize the film easily. And after tuning the growth condition, pressure, temperature, or even substrate temperature, whatever, then we can finally get some desired film. Then you can see that the efficiency significantly rely on the film, the crystal orientation and the crystallinity. It's a very critical growth condition for the substrate temperature or the source temperature and also the film thickness. And particularly, this needs a lot of work, and the screening process is pretty painful. But once you get a good quality film, and our initial film is very low efficiency, roughly 6 years ago, it's only around 4%. But gradually, So gradually, if we do further engineer the whole process, we can get roughly around 8%. So imagine that this is just the pure film without any engineering yet. Even we call it a gross interface, it's barely like the 8% of cadmium telluride 50 years ago. It's just to gross the film and make a simple device. And gradually, I think this is a very promising solar techniques. Pretty stable in air, not like the perovskite. Pretty wide band gap can be further tuned. So this is a very nice technique, and we continue work this. And based on the prediction, and even Dr. Hall and working in this area using the different techniques, right? So I think this material growth approach and device architecture manufacturing manipulation. So this could correct a very wide area for this material. And overall, it's predicted that can be 20 or 25% by surprise about the defect inside. Because the crystal structure different to the cadmium telluride, the inside chemistry, defect chemistry is different to the cadmium telluride. And imagine that the cadmium telluride incorporate about the cadmium chloride treatment, the back contact and the dopings. So I think that's this is a long run to further improve the device efficiency, but we have a good role model, right? So that will be good to further work in this area to further control the device and the defect. Hope so that we can realize certain of the good efficiency soon. And last, I'm spending several minutes to talk about a new techniques. Perovskite, the whole PV area, crazy for the perovskite in the past 10 years. Actually, our group is a follower, not involved in this area. But once there is some promising rising star, everyone want to try this, right? So how is happen this one? So major of the perovskite briefly is the organic, inorganic hybrid solar techniques. It can be the same device architecture like cadmium telluride, like the silicon, or like the organic PV, whatever. So, but promising thing is that its efficiency improved from 3% to 26% in roughly 10 years. This is amazing, right? So how this realize this one, the whole area do not expect this significant improvement initially, but it's have a lot of new knowledge introduced and learned. So we also try to learn from these techniques. But this material, not like the silicon, not like the cadmium telluride or other chalcogenide, it's unstable in air, in heat, in moisture. It's like a kid. He even have some talent, but his body is not that strong, right? But how we can work on this area, that's why we focus on how we can make it stable. The first thing we try to understanding why it's not stable, because it have some crystalline structure issue, it have some device design issue. Traditionally, they have two major ways to grow this perovskite. For the solution process, including the spin coating, the black coating, straw die coating, we are not, to be honest, I'm not expert on this area. So we are initial a new project try to using the vapor, physical vapor deposition, but it's pretty challenging because difficult to control. Compared to the cadmium telluride, we can see that it melt above 1000 degrees, right? For the antimony selenide, it can be melt around 600. But this one only 100 or 200 it melt. So it's not mean the lower the better, but the lower the challenger to control it. So that's why this material majorly still using the solution process. But gradually, if we want to integrate this technique to the larger area of other solar techniques, vapor deposition probably a good way because it's easier to scale up to the existing thin film solar techniques. briefly, for my group recently work on, we call it copper electrode. Very simple, borrow from the solution and try to retire the gold or silver electrode in the NIP structure because we have limited people working on this area. One way is try to reduce the cost for manufacturing because we know that the carbon is dirty cheap, right? So it's just thousands or 10,000 cost compared to the gold or other metal. And here we initially very simple device architecture, but recently we can demonstrate around 20% using the carbon. So it's a pretty cheaper approach. And compared to the gold, the carbon demonstrates desired stability because the carbon electrode can repel the moisture based on its hydrophobic behavior. And also some other technique is that the Perovskite, we also send ourselves to the International Space Station through the collaboration with the NASA. So 2 years ago, during the COVID, my students drive the cell to the NASA's center. So they're shooting this cell and spending around half a year. So I got this cell back last year, but I haven't opened the bag because the moisture not that easy to control so far. Another thing is that we try to grow larger area, try to extend from a small area to the larger area. So we working on the 5 by 5 or 10 by 10 level module using the solution process. It's just initial this the one and got some funding from the National Science Foundation to try ours to make this one. So this is the group working on this area. So overall, I think this is the 3 or 2 thin film solid techniques we are working on and try to contribute to this area. And gradually, all the challenges in the thin film techniques should be similar, and how to control the defect, how to build a stable device, or even control about the carrier transport. So we hope to try to further improve the device performance and try to build the connection with the industry partners, try to transfer the techniques from our lab to the industry. So this is the thin film solid techniques I try to share here, and I really appreciate this opportunity to be here and appreciate the funding agency from the different agency and also the collaborator. So hope to work with Dr. Hall here to further improve the device and yeah, that's it. Thank you very much. Yeah.
I think like it took us actually quite a long time to understand the evolution history of a copper.
Oh, yeah.
So you explained very clearly and very well here. So now I think the talk is open for question and discussion. Any question?
Yeah.
About the group 5 element doping. I see you tried different elements in the work.
Yes.
You tried.
Here it is. Yeah. So initially we tried the arsenic, and then because arsenic was demonstrated in the here. Yeah. This work was in situ doping. Work on using the cadmium arsenide to dope, and then we focused on the arsenic initially. But during our work, we also try to using the different. We also try to using the different, for example, phosphor antimony bismuth. We demonstrate this work is in revision, but it's a different bismuth salt. Yeah, we are using. Right?
Yeah. I mean, which element do you find is better for the doping, and what's the main function? Because as you said from the beginning, the polycrystalline cadmium telluride, the main problem comes from the green boundaries because you have a lot of green boundary compared to the mono green.
Yes.
So is this doping help to pass with the green boundary or help to like the greens recrystallize?
Yes or no? Yes means that go back to the first question, which element we try. We try all of them. We play with 20 or 30 chemicals. To be honest, this is the advantage of working in the lab. You can for the second question, which one is desired? Based on my understanding, probably the phosphor arsenic easier to introduce because it have a relatively smaller ionic radiance and higher diffusivity in the device. For the antimony and the bismuth, it's relatively large ion radiance and heavy. So that means it's difficult to drive it. Particularly, we prefer a low temperature. Why? Because the previous cadmium chloride, for example, that's the activation process. We call it around 400 degrees C. So that means we do not want to over that temperature to damage the cadmium chloride treated film. So that's why for the antimony bismuth may close to 400, but it's may have some risk to damage the previous treated film. That's why for phosphine or arsenic can be controlled lower than or close to 300. So that gives us a temperature gap to protect the previous process. Yeah. And the third question is for the passivation in the green boundary. We do not call it passivation because it's a little bit a long history why we do the polycrystalline, because they have a long time debate why the green boundary normally we consider it's a defect, it's bad, it's a recombination site. But in the cadmium telluride, passivation using the cadmium chloride is pretty effective. The green boundary, the reach of chlorine segregate against the green boundary, but the cadmium will diffuse well. This is also the initial idea why we using the arsenic chloride or other group 5 halide. We call it group that they have many candidates. The defect environment or the defect chemistry different between the green boundary and the green inner. So that's correct the chance to leverage about the advantage in the green boundary. For example, the green boundary is relatively cadmium poor and cadmium rich, because that's have more cadmium introduced inside. And after the cadmium chloride treatment, then the chlorine segregate against the green boundary, then when introduced about the actin, that probably easier to hold in the green boundary than further diffuse into the green inner. Yeah.
A further question. For the cadmium chloride treatment, you don't see the green growth after the...
Oh yeah. Cadmium chloride have several roles. One of the major role is green growth. That's true. The as deposit, for example, using the CSS or the VTD, probably the as deposit film only around 1 micrometer or smaller, but the cadmium chloride treatment will be further growth and recrystallize the grain into 2, 3, 5, or even we can get 10 micrometer large grain. So it's depending on the treatment condition. Yeah. So that's why the passivation majorly finished after the cadmium chloride. So that's why cadmium chloride treatment is pretty magic for the CAD-TEL. If you check about the efficiency chart, that's significant, can be double almost. Yeah. So it's a pretty amazing process. Yeah. But it's come from an accident because some people probably threw some cadmium chloride in the processing line, so then they revisited the process to get it. Yeah.
Thank you.
Yeah. Any other questions? I think I have a follow-up question with that one. So sure. Basically, cadmium chloride, we mentioned about like 2 functions. One function is making the grain bigger, like particularly lateral grain, right? Yeah. Lateral grain size. You mentioned about like a 5 or even to 10 micron. And also another function is probably like a green boundary passivation. Yes. I'm just wondering, have we really like a sort of like a quantify or like a in other way to see which actually function have the dominant role in terms of the efficiency improvement? Because I think we had the test drive workshop in end of June. We talk about actually HZB is working on like the green boundary impact. So so they actually mentioned about like the green boundary, particularly like the density of green boundary have a big issue in terms of open circuit voltage. In addition to like we're talking about like a green boundary passivation. So we are just thinking like whether this is actually a typical case for all the polycrystalline.
Yeah, that's true. I agree that I remember there is one of my colleagues at NREL, they compared the CAD-TEL, compare the Perovskite, or even the CIGS. So they find the similar role for the because chlorine it's a 2D material. So they go back to the CAD-TEL, cadmium chlorine treatment in the different languages. For example, material science guy like green growth, green recrystallization. The physics guy probably like passivation. The chemistry guy probably talk about the defect. But overall, I think, they're hybrid together. Passivation, if we talk about the passivation, because the green boundary have a lot of dangling bond, right? So that's the defect. If we from the material science, we can see the major role of the cadmium chloride is try to green growth and reduce the structure defect. Structure defect including the stacking fault, dislocation, and also a lot of physical void probably. So this is the material science guy working on this area. Observe the grain size growth, the grain boundary, the stacking fault using the TEM or whatever. And for the physics guy, they talk about the passivation and recommendation, the carrier, how they transport in the grain boundary. That's true. The passivation role is significant. We can see that before and after the cadmium chlorine treatment, the carrier lifetime can be significantly jump, and order 1 or 2 order of magnitude improve. And also from the chemistry, like what I mentioned, the chlorine. Actually, we can see the defect inside the chlorine segregate. There is the DFT calculation. The chlorine also present as the N-type doping actually. It's significant if you check about the element distribution. So overall, it's not a single role, like we mentioned. It may not be only limited to the cadmium telluride. And for the perovskite, probably the Ma chloride, right? For the CIGS, probably some potassium element. So I think this is corresponding to individual absorber should have a corresponding chemical, known or unknown, to realize this role. That's a pretty unified concept probably. Some groups call it flux that will melt during the chlorine treatment, and then green growth, then passivation, then doping realize the combined together. Yeah.
Another follow-up question actually with the one. So did we see, because now we have the chemiluminescence under the SEM. So basically you can do or even the TRCL, time resolved chemiluminescence under the SEM. Basically what you can see is you can see the the recombination within the green interior and the green boundary. Yeah. So my further follow-up question, I'm not quite sure whether that has been done, but I believe it has already been done. So my follow-up question would be actually after cadmium chlorine treatment, did we actually see in terms of like a green interior, even the green interior, like the CL intensity or even the lifetime have increased? Because you talk about like the flux. One flux, the major role is you're also talking about like the structure crystalline defect, right? Yeah. So if you already decrease the crystalline defect, you should also see a lifetime increase in the green interior. In addition, like something magic happen at the green boundary. Like for example, we talk about like chlorine at the accumulation at the green boundary. So I think my question is, have we quantify the real contribution from this?
That's a very interesting. That's a very interesting topic. How to distinguish or differentiate about the green boundary and the green inner? It's pretty challenging, like the EL or CL or TRPL or whatever the mapping techniques, right? Like we mentioned that green size can be controlled from 1 to 10 micrometer. But the green boundary probably just several nanometer. From the EL or PL, we can see clearly that the chlorine segregate against the green boundary, which is corresponding to the improved or reduced CL or EL signal. But for the fundamental, how the green inner improved, probably to me, I think the resolution probably not that significant like the green boundary, because the dominant, you can see it's bright if you check about the EL, right? So that's why we try to work when we have a researcher try to grow the single crystal cattail using the MBE. It's ongoing, try to see how this treatment could be impacted the green inner. If we can grow a single crystal, then we can imagine that's a bigger green inner, right?
You mentioned about like the VOC improvement.
Yeah.
The single crystal.
That's one of the challenges, how to transfer the learning from the single crystal to the polycrystalline. It's a huge challenge because they have around 200 m wall gap, right? But we are working on that to fill that gap. Yeah.
Another question you mentioned about doping. So Kevin asked about like you use a different group 5 for it's to increase the carrier concentration. So you talk about like the actually the pros and the cons for the phosphorus, arsenide, and germanium and the bismuth. I just got one question. Have we calculated the activation energy required for this element? For example, you mentioned about also the temperature limitation, for example, not above 400 degrees, right? So is there like a theoretical calculation, say which one have a lower activation energy to be activated?
Yes, not in my group, but this is the document by previously maybe 5. I cannot remember exactly that. That did both polycrystalline and single crystal, because cadmium telluride can be purchased as a larger single crystal. But the challenging part, like mentioned, for the single crystal, need a high temperature, about 500 or 600 degrees C, to drive this one. And the challenger, that's true. The heavy the element, the difficult is the diffusivity. Yeah, that's why how to drive the element to segregate in the green boundary to the green inner, need to tune the processing window. Yeah, so that's. But overall, I think not only about the element, it's also rely on the treatment environment.
Yeah, exactly.
Yeah, that's another challenger. Need to tune a lot of our conditions, try to make this element in the desire. Like the defect calculation, for example, here is one example to calculate the phosphor and arsenic, right? So you can see that in the cadmium rich and tellurium rich, there will have the different defect formation energy. So that will be the different. That's why that probably need to correct the cadmium rich condition to drive the element much easier. Yeah. So overall, it's a pretty critical. Get a precise control of this the dopant precursor selection and the process that need to hybrid together. Yeah. So
Okay.
Pretty challenging work. Yeah.
That's very interesting. I just want to have a double check whether we have any other question. Okay, so if not, I just want to thanks Dr. Yan again for the excellent talk, and also I think it's a great opportunity to have some research exchange, particularly for our students come to visit us. We also looking forward to more undergraduate students from ASU to come to spring, and so we can have more like a discussion and a collaboration in the future. Please join me to thank Dr. Yan again for the excellent talk.
Yeah. Thank you. Thank you very much. Yeah.